Chapter 9. Fluid Lines and Fittings. Introduction. Aircraft fluid lines are usually made of metal tubing or flexible hose. Metal tubing, also called rigid fluid lines, is used in stationary applications and where long, relatively straight runs are possible. They are widely used in aircraft for fuel, oil, coolant, oxygen, instrument, and hydraulic lines. Flexible hose is generally used with moving parts, or where the hose is subject to considerable vibration. Occasionally, it may be necessary to repair or replace damaged aircraft fluid lines. Very often the repair can be made simply by replacing the tubing. However, if replacements are not available, the needed parts may have to be fabricated. Replacement tubing should be of the same size and material as the original tubing. All tubing is pressure tested prior to initial installation, and is designed to withstand several times the normal operating pressure to which it is subjected. If a tube bursts or cracks, it is generally the result of excessive vibration, improper installation, or damage caused by collision with an object. All tubing failures should be carefully studied and the cause of the failure determined. 9-1. Rigid fluid lines. Tubing materials. Copper. In the early days of aviation, copper tubing was used extensively in aviation fluid applications. In modern aircraft, aluminum alloy, corrosion-resistant steel, or titanium tubing have generally replaced copper tubing. Aluminum alloy tubing. Tubing made from 1100 H14, 1/2 hard, or 3003 H14, 1/2 hard, is used for general-purpose lines of low or negligible fluid pressures, such as instrument lines and ventilating conduits. Tubing made from 2024-T3, 5052O, and 6061-T6 aluminum alloy materials is used in general-purpose systems of low and medium pressures, such as hydraulic and pneumatic 1000 to 1500 psi systems, and fuel and oil lines. Steel. Corrosion-resistant steel tubing, either annealed KERS 304, KERS 321, or KERS 304-1/8 hard, is used extensively in high-pressure hydraulic systems, 3000 psi or more, for the operation of landing gear, flaps, brakes, and in fire zones. Its higher tensile strength permits the use of tubing with thinner walls. Consequently, the final installation weight is not much greater than that of the thicker wall aluminum alloy tubing. Steel lines are used where there is a risk of foreign object damage. FUD, that is, the landing gear and wheel well areas. Swaged or MS Pluralist fittings are used with corrosion-resistant tubing. Although identification markings for steel tubing differ, each usually includes the manufacturer's name or trademark, the Society of Automotive Engineers, C number, and the physical condition of the metal. Titanium 3AL-2.5V. Titanium 3AL-2.5V tubing and fitting is used extensively in transport category and high-performance aircraft hydraulic systems for pressures above 1500 psi. Titanium is 30% stronger than steel, and 50% lighter than steel. Offutt fittings, or swaged fittings are used with titanium tubing. Do not use titanium tubing and fittings in any oxygen system assembly. Titanium and titanium alloys are oxygen reactive. If a freshly formed titanium surface is exposed in gaseous oxygen, spontaneous combustion could occur at low pressures. Material identification. Before making repairs to any aircraft tubing, it is important to make accurate identification of tubing materials. Aluminum alloy, steel, or titanium tubing can be identified readily by sight where it is used as the basic tubing material. However, it is difficult to determine whether a material is carbon steel or stainless steel, or whether it is 1100, 3003, 5052-0, 6061-T6, or 2024-T3 aluminum alloy. To positively identify the material used in the original installation, compare code markings of the replacement tubing with the original markings on the tubing being replaced. On large aluminum alloy tubing, the alloy designation is stamped on the surface. On small aluminum tubing, the designation may be stamped on the surface, but more often it is shown by a color code, not more than 4 in width, painted at the two ends, and approximately midway between the ends of some tubing. When the band consists of 2 colors, only half the width is used for each color. Figure 9-1. If the code markings are hard or impossible to read, it may be necessary to test samples of the material for hardness by hardness testing. Sizes. Metal tubing is sized by outside diameter, OD, which is measured fractionally in 1/16 of an inch. For example, number 6 tubing is 6/16 or 3/8, and number 8 tubing is 8/16 or 1/2, and so forth. The tube diameter is printed on all rigid tubing. In addition to other classifications or means of identification, tubing is manufactured in various wall thicknesses. Thus, it is important when installing tubing to know not only the material and outside diameter, but also the thickness of the wall. The wall thickness is printed on the tubing in thousandths of an inch. To determine the inside diameter, ID, of the tube, subtract twice the wall thickness from the outside diameter. For example, a number 10 piece of tubing with a wall thickness of 0.063 has an inside diameter of 0.625 minus 2, 0.063 equals 0.499. Fabrication of metal tube lines. Damaged tubing and fluid lines should be repaired with new parts, whenever possible. Unfortunately, sometimes replacement is impractical, and repair is necessary. Scratches, abrasions, or minor corrosion on the outside of fluid lines may be considered negligible and can be smoothed out with aluminum alloy number color of band 1100 white 3003 green 2014 gray 2024 red 5052 purple 6053 black 6061 blue and yellow 7075 brown and yellow. Figure 9-1. Painted color codes used to identify aluminum alloy tubing. 9-2. Cut. A burnishing tool or aluminum wool. Limitations on the amount of damage that can be repaired in this manner are discussed in this chapter under rigid tubing inspection and repair. If a fluid line assembly is to be replaced, the fittings can often be salvaged. Then the repair involves only tube forming and replacement. Tube forming consists of 4 processes: cutting, bending, flaring, and beating. If the tubing is small and made of soft material, the assembly can be formed by hand bending during installation. If the tube is 1/4 diameter or larger, and bending without the aid of tools is impractical. Tube cutting. When cutting tubing, it is important to produce a square end, free of burrs. Tubing may be cut with a tube cutter or a hacksaw. The cutter can be used with any soft metal tubing, such as copper, aluminum, or aluminum alloy. Correct use of the tube cutter is shown in figure 9-2. Special chitless cutters are available for cutting aluminum 6061-T6, corrosion-resistant steel, and titanium tubing. A new piece of tubing should be cut approximately 10% longer than the tube to be replaced to provide for minor variations in bending. Place the tube in the cutting tool with the cutting wheel at the point where the cut is to be made. Rotate the cutter around the tubing, applying light pressure to the cutting wheel by intermittently twisting the thumb screw. Too much pressure on the cutting wheel at one time could deform the tubing or cause excessive burring. After cutting the tubing, carefully remove any burrs from inside and outside the tube. Use a knife or the burring edge attached to the tube cutter. The deburring operation can be accomplished by the use of a deburring tool. Figure 9-3. This tool is capable of removing both the inside and outside burrs by just turning the tool end for end. When performing the deburring operation, use extreme care that the wall thickness of the end of the tubing is not reduced or fractured. Very slight damage of this type can lead to fractured flares or defective flares, which do not seal properly. Use a fine-tooth file to file the end square and smooth. If a tube cutter is not available, or if tubing of hard material is to be cut, use a fine-tooth hacksaw, preferably one having 32 teeth per inch. The use of a saw decreases the amount of work hardening of the tubing during the cutting operation. After sawing, file the end of the tube square and smooth, removing all burrs. An easy way to hold small diameter tubing, when cutting it, is to place the tube in a combination flaring tool and clamp the tool in a vise. Make the cut about 1/2 inch from the flaring tool. This procedure keeps sawing vibrations to a minimum, and prevents damage to the tubing, if it is accidentally hit with the hacksaw frame or file handle while cutting. Be sure all filings and cuttings are removed from the tube. Tube bending. The objective in tube bending is to obtain a smooth bend without flattening the tube. Tubing under 1/4 in diameter usually can be bent without the use of a bending tool. For larger sizes, either portable hand benders or production benders are usually used. Figure 9-4 shows preferred methods and standard bend roddy for bending tubing by tube size. Using a hand bender, insert the tubing into the groove of the bender, so that the measured end is left of the formed block. Align the 2 zeros and align the mark on the tubing with the L on the form handle. If the measured end is on the right side, then align the mark on the tubing with the rotate toward open side of cutter. Tube clean cut. Figure 9-2. Tube cutting. Figure 9-3. Deburring tool. 9-3. A hand-B portable hand benders C production bender. Type bender ABBBBBCBBCBBCCBCC. Tubo D tilde slash dot above hot check. 1/4. Karen slash dot above hot check. Slash dot above hot check. 1/2. Karen slash 3/4. Standard bend slash dot above hot check. Dot above hot check. Tilde slash dot above hot check. Tilde slash dot above hot check. Tilde Karen slash dot above hot check. 1/1. and 1/2, 1 and 1/4, 2, 1 and 1/2, 2 and 1/2, 1 and 3/4. Type bender CBCCCCCCCCCCC. Tube OD/1, 1, 1 tilde slash, 1 and 1/4, 1/1/1 and 1/2, 1 and 1/2, 1 and 3/4, 2, 2 and 1/2, 3, standard bend 2, 3 and 1/2, 3, 3 and 1/2, 3 and 3/4, 5, 6, 5, 6, 7, 8, 10, 12. Figure 9-4. Standard bend Radi tools. Bending tools form the various sizes of tubes. Are on the form handle. With a steady motion, pull the form handle until the 0 mark on the form handle lines up with the desired angle of bend, as indicated on the radius block. Figure 9-5. And benders come in different sizes that correspond to the tube diameter. Make sure to select the correct bender for the desired tube diameter. Figure 9-6 shows hand benders available for different sizes of tubing. Typically, the tubing size is stamped in the bender. Figure 9-7. Bend the tubing carefully to avoid excessive flattening, kinking, or wrinkling. A small amount of flattening in bends is acceptable, but the small diameter of the flattened portion must not be less than 75% of the original outside diameter. Tubing with flattened, wrinkled, or irregular bends should not be installed. Wrinkled bends usually result from trying to bend thin wall tubing without using a tube bender. Excessive flattening causes fatigue failure of the tube. Examples of correct and incorrect tubing bends are shown in Figure 9-8. Tube bending machines for all types of tubing are generally used in repair stations and large maintenance shops. With such equipment, proper bends can be made on large diameter tubing, and on tubing made from hard material. The production CNC trademark tube bender is an example of this type of machine. Figure 9-9. The ordinary production tube bender accommodates tubing ranging from 1/4 to 1 1/2 outside diameter. Benders for larger. Figure 9-6. And benders. Figure 9-7. Size identification. Sizes are available, and the principle of their operation is similar to that of the hand tube bender. The radius blocks are so constructed that the radius of bend varies with the tube diameter. The radius of bend is usually stamped on the block. Figure 9-5. Tube bending. 9-4. Perfect bend, flattened bend. Good. Wrinkled bend, kinked bend. Figure 9-8. Correct and incorrect tubing bends. Alternative bending methods. When hand or production tube benders are not available, or are not suitable for a particular bending operation, a filler of metallic composition, or of dry sand may be used to facilitate bending. When using this method, cut the tube slightly longer than required. The extra length is for inserting a plug, which may be wooden, in each end. The tube can also be closed by flattening the ends, or by soldering metal discs in them. After plugging one end, fill and pack the tube with fine, dry sand and plug tightly. Both plugs must be tight so they are not forced out when the bend is made. After the ends are closed, bend the tubing over a forming block shaped to the specified radius. In a modified version of the filler method, a fusible alloy is used instead of sand. In this method, the tube is filled under hot water with a fusible alloy that melts at 160 degrees Fahrenheit. The alloy-filled tubing is then removed from the water, allowed to cool, and bent slowly by hand around a forming block or with a tube bender. After the bend is made, the alloy is again melted under hot water and removed from the tubing. When using either filler methods, make certain that all particles of the filler are removed. Visually inspect with a borescope to make certain that no particles are carried into the system in which the tubing is installed. Store the fusible alloy filler where it is free from dust or dirt. It can be ray-melted and Figure 9-9. CNC trademark tube bending machine. Reused as often as desired. Never heat this filler in any other way than the prescribed method, as the alloy will stick to the inside of the tubing, making them both unusable. Tube flaring. Two kinds of flares are generally used in aircraft tubing, the single flare and the double flare. Figure 9-10A and B flares are frequently subjected to extremely high pressures. Therefore, the flare on the tubing must be properly shaped or the connection leaks or fails. A flare made too small produces a weak joint, which may leak or pull apart. If made too large, it interferes with the proper engagement of the screw thread on the fitting and causes leakage. A crooked flare is the result of the tubing not being cut squarely. If a flare is not made properly, flaws cannot be corrected by applying additional torque when tightening the fitting. The flare and tubing must be free from cracks, dents, nicks, scratches, or any other defects. The flaring tool used for aircraft tubing has male and female dies ground to produce a flare of 35 degrees to 37 degrees. Under no circumstance is it permissible to use an automotive type flaring tool that produces a flare of 45 degrees. Figure 911, the single flare hand flaring tool, similar to that shown in Figure 9-12, is used for flaring tubing. The tool consists of a flaring block or grip die, a yoke, and a flaring pin. The flaring block is a hinged double bar with holes corresponding to various sizes of tubing. These holes are countersunk on one end to form the outside support against which the flare is formed. The yoke is used to center the flaring pin over the end of the tube to be flared. Two types of flaring tools are used to make flares on tubing: the impact type and the rolling type. 9-5. 37 degrees. A. Single flared end. B. Double flared end. Figure 9-10. Cutaway view of single flared A and double flared B tube ends. Instructions for rolling type flaring tools. Use these tools only to flare soft copper, aluminum, and brass tubing. Do not use with corrosion-resistant steel or titanium. Cut the tube squarely and remove all burrs. Slip the fitting nut and sleeve on the tube. Loosen clamping screw used for locking the sliding segment in the die holder. This permits their separation. The tools are self-gauging. The proper size flare is produced when tubing is clamped flush with the top of the die block. Insert tubing between the segments of the die block that correspond to the size of the tubing to be flared. Advance the clamp screw against the end segment and tighten firmly. Move the yoke down over the top of the die holder and twist it clockwise to lock it into position. Turn the feed screw down firmly, and continue until a slight resistance is. Figure 911. Flaring tool. Felt. This indicates an accurate flare has been completed. Always read the tool manufacturer's instructions, because there are several different types of rolling type flaring tools that use slightly different procedures. Double flaring. A double flare is used on soft aluminum alloy tubing 3/8 outside diameter and under. This is necessary to prevent cutting off the flare and failure of the tube assembly under operating pressures. A double flare is smoother and more concentric than a single flare and therefore seals better. It is also more resistant to the shearing effect of torque. Figure 9-12. Hand flaring tool. 9-6. Double flaring instructions. Deburr both the inside and outside of the tubing to be flared. Cut off the end of the tubing, if it appears damaged. Anneal brass, copper, and aluminum by heating to a dull red and cool rapidly in cold water. Open the flaring tool by unscrewing both clamping screws. Select the hole in the flaring bar that matches the tubing diameter, and place the tubing with the end you have just prepared, extending above the top of the bar by a distance equal to the thickness of the shoulder of the adapter insert. Tighten clamping screws to hold tubing securely. Insert pilot of correctly sized adapter into tubing. Slip yoke over the flaring bars and center over adapter. Advance the cone downward until the shoulder of the adapter rests on the flaring bar. This bells out the end of the tubing. Next, back off the cone just enough to remove the adapter. After removing the adapter, advance the cone directly into the belled end of the tubing. This folds the tubing on itself and forms an accurate double flare without cracking or splitting the tubing. To prevent thinning out of the flare wall, do not over-tighten. Figure 9-13. Fittings. Rigid tubing may be joined to either an end item, such as a brake cylinder, another section of either rigid tubing, or to a flexible hose, such as a drain line. In the case of connection to an end item or another tube, fittings are required, which may or may not necessitate flaring of the tube. In the case of attachment to a hose, it may be necessary to be the rigid tube so that a clamp can be used to hold the hose onto the tube. Pluralist fittings. Although the use of Pluralist tube fittings eliminates all tube flaring, another operation, referred to as presetting, is necessary prior to installation of a new Pluralist tube assembly. Pluralist tube assemblies should be preset with the proper size presetting tool or operation. Figure 9-14. Steps 1, 2, and 3 illustrates the presetting operation, which is performed as follows. 1. Cut the tube to the correct length, with the ends perfectly square. Deburr the inside and outside of the tube. Slip the nut. Then the sleeve. Over the tube. Step 1. Lubricate the threads of the fitting and nut with hydraulic fluid. 2. Place the fitting in a vise. Step 2. And hold the tubing firmly and squarely on the seat in the fitting. The tube must bottom firmly in the fitting. Tighten the nut until the cutting edge of the sleeve grips the tube. To determine this point, slowly turn the tube back and forth while tightening the nut. When the tube no longer turns, the nut is ready for tightening. 3. Final tightening depends upon the tubing. Step 3. For aluminum alloy tubing up to and including 1/2 outside diameter, Tighten the nut from 1 to 1 1/6 turns. For steel tubing and aluminum alloy tubing over 1/2 outside diameter, tighten from 1 1/6 to 1 1/2 turns. After presetting the sleeve, disconnect the tubing from the fitting and check the following points. The tube should extend 3/30 seconds to 1/8 beyond the sleeve pilot. Otherwise, blow-off may occur. The sleeve pilot should contact the tube or have a maximum clearance of 0.005 for aluminum alloy tubing or 0.015 for steel tubing. A slight collapse of the tube at the sleeve cut is permissible. No movement of the sleeve pilot, except rotation, is permissible. Beading. Tubing may be beaded with a hand beading tool, with machine beading rolls, or with grip dies. The method to be used depends on the diameter and wall thickness of the tube and the material from which it was made. The hand beading tool is used with tubing having 1/4 to 1 outside diameter. Figure 9-15. The bead is formed by using the beater frame with the proper rollers attached. The inside and outside of the tube is lubricated with light oil to reduce the friction between the rollers during beading. The Figure 9-13. Double flare tool. 9-7. Tilde/. To dot above / hot check. Step 1. Fitting. Sleeve tube nut. Sleeve pilot tube. Sleeve cutting edge. Step 2. Step 3. Slight deformation permissible 0.005. Maximum aluminum alloy tubing. 0.015. Maximum corrosion resistant steel tubing. Sizes, marked in 1/16 of an inch on the rollers, are for the outside diameter of the tubing that can be beaded with the rollers. Separate rollers are required for the inside of each tubing size, and care must be taken to use the correct parts when beading. The hand beading tool works somewhat like the tube cutter in that the roller is screwed down intermittently while rotating the beading tool around the tubing. In addition, a small vise tube holder is furnished with the kit. Other methods and types of beading tools and machines are available, but the hand beading tool is used most often. As a rule, beading machines are limited to use with large diameter tubing, over 1 15/16, unless special rollers are supplied. The grip die method of beading is confined to small tubing. Fluid line identification. Fluid lines in aircraft are often identified by markers made up of color codes, words, and geometric symbols. These markers identify each line's function, content, and primary hazard. Figure 9-16 illustrates the various color codes and symbols used to designate the type of system and its contents. Fluid lines are marked, in most instances, with 1 tape or decals. Figure 9-17A on lines 4 in diameter, or larger lines in oily environment, hot lines, and on some cold lines. Steel tags may be used in place of tape or decals. Figure 9-17B paint is used on lines in engine compartments where there is the possibility of tapes, decals, or tags being drawn into the engine induction system. In addition to the above-mentioned markings, certain lines may be further identified regarding specific function within a system, for example, drain, vent, pressure, or return. Lines conveying fuel may be marked FLAM, figure 9-17. Lines containing toxic materials are marked toxic in place of FLAM. Lines containing physically dangerous materials, such as oxygen, nitrogen, or Freon TM, may be marked FDN. Aircraft and engine manufacturers are responsible for the original installation of identification markers, but the aviation mechanic is responsible for the replacement when it becomes necessary. Tapes and decals are generally placed on both ends of a line, and at least once in each compartment through which lines run. In addition, identification markers are placed immediately adjacent to each valve, regulator, filter, or other accessories within a line. Where paint or tags are used, location requirements are the same as for tapes and decals. Figure 9-14. Presetting Pluralist tube assembly. 9-8. Figure 9-15. To use the hand beading tool, cut with tube cutter, 1. Deburr 2. Oil 3. And revolve tool around tube, while tightening handle, 4. Fluid line and fittings. Depending on the type and use, fittings have either pipe threads or machine threads. Pipe threads are similar to those used in ordinary plumbing and are tapered, both internal and external. External threads are referred to as male threads and internal threads are female threads. When two fittings are joined, a male into a female, the thread taper forms a seal. Some form of pipe thread lubricant approved for a particular fluid application should be used when joining pipe threads, to prevent seizing and high-pressure leakage. Use care when applying thread lubricant, so that the lubricant does not enter and contaminate the system. Do not use lubricants on oxygen lines. Oxygen reacts with petroleum products and can ignite. Special lubricants are available or oxygen systems. Machine threads have no sealing capability and are similar to those used on common nuts and bolts. This type of fitting is used only to draw connections together or for attachment through bulkheads. A flared tube connection, a crush washer, or a synthetic seal is used to make the connection fluid tight. Machine threads have no taper and do not form a fluid tight seal. The size of these fittings is given in dash numbers, which equal the nominal outside diameter in 1/16 of an inch. Universal bulkhead fittings. When a fluid line passes through a bulkhead, and it is desired to secure the line to the bulkhead, a bulkhead fitting should be used. The end of the fitting that passes through the bulkhead is longer than the other ends, which allows a lock nut to be installed, securing the fitting to the bulkhead. Fittings attach one piece of tubing to another or to system units. There are 4 types. 1. Bead and clamp. 2. Flared fittings. 3. Pluralist fittings. And 4. Permanent fittings. Perma-Swag trademark, Permalite trademark, and Offutt trademark. The amount of pressure that the system carries and the material used are usually the deciding factors in selecting a connector. The beaded type of fitting, which requires a bead and a section of hose and hose clamps, is used only in low or medium pressure systems, such as vacuum and coolant systems. The flared, pluralist, or permanent type fittings may be used as connectors in all systems, regardless of the pressure. And flared fittings. A flared tube fitting consists of a sleeve and a nut. Figure 9-18. The nut fits over the sleeve and, when tightened, draws the sleeve and tubing flare tightly against. 9-9. Water injection. Water injection. Water injection. Compressed gas. Compressed gas. Compressed gas. Coolant, coolant, coolant. Fuel. 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 Electrical conduit. Electrical conduit. Electrical conduit. Instrument air. Instrument air. Instrument air. Lubrication, lubrication, lubrication. Rocket oxidizer. Rocket oxidizer. Rocket oxidizer. Air condition. Air condition. Air condition. Hydraulic, hydraulic, hydraulic. Rocket fuel. Rocket fuel. Rocket fuel. Instrument air. Instrument air. Instrument air. Hydraulic, hydraulic, hydraulic. Breathing oxygen. Breathing oxygen. Breathing oxygen. Fuel, fuel. Flam, flam. A. De-icing, de-icing, de-icing. Fire protection. Fire protection. Fire protection. Fuel flam. B. Figure 9-17. Fluid line identification using tape and decals, A, and metal tags. B. Fitting combinations composed of different alloys should be avoided to prevent dissimilar metal corrosion. As with all fitting combinations, ease of assembly, alignment, and proper lubrication should be assured when tightening fittings during installation. Standard and fittings are identified by their black or blue color. All in steel fittings are colored black. All in aluminum fittings are colored blue, and aluminum bronze fittings are cadmium plated and natural in appearance. A sampling oven fittings is shown in Figure 9-19. Figure 9-20 contains additional information on sizes, torques, and bend radi. And flared fittings are different from MS Pluralist fittings, and they are not interchangeable. And flared fittings are easily recognized, because they have a cone at the end of the fitting, while the MS Pluralist fitting has a straight end. Figure 9-21, an 819 sleeve. Warning symbol. Figure 9-16. Identification of aircraft fluid lines. A male fitting to form a seal. Tubing used with this type of fitting must be flared before installation. The male fitting has a cone-shaped surface with the same angle as the inside of the flare. The sleeve supports the tube so that vibration does not concentrate at the edge of the flare and distributes the shearing action over a wider area for added strength. Tubing. An 818 nut. Figure 9-18. Flared tube fitting. 9-10. An 744 to An 932. Material. Aluminum alloy. Code D. Steel. Code. Absence of letter. Brass. Code B. Aluminum bronze. Code Z for an 819 sleeve. Size. The dash number following the N number indicates the size of the tubing, or hose, for which the fitting is made in 16 ths of an inch. This size measures the outer diameter of tubing, and the inner diameter of hose. Fittings that have pipe threads are coded by a dash number, indicating the pipe size in 8 ths of an inch. The material code letter, as noted above, follows the dash number. Bolt AN 774, Bolt AN 775, elbow AN 776, elbow AN 777, elbow AN 778, T AN 779. Plug AN 806, Union AN 815. Nut AN 817. Sleeve AN 819. TAN 804. Plug AN 814. Adapter AN 807. Nipple AN 816. Cap AN 820. Nut AN 818. Elbow AN 821. Elbow AN 823. TAN 825. Cross AN 827. Union AN 832. Elbow AN 822. TAN 824. TAN 826. Elbow AN 838. Elbow AN 839. Elbow AN 833. TAN 834. Figure 9-19. And standard fittings. Elbow AN 837. 911. Tubing outer diameter. Inches. Fitting bolt or nut size. Aluminum alloy tubing. Bolt, fitting, or nut torque, in pounds. Steel tubing. Bolt fitting, or nut torque, in pounds. Hose end fittings and hose assemblies. MS28740 or equivalent end fitting. Alum. Alloy 1100-H14. 5052-0. Minimum bend Roddy. Inches, steel minimum maximum. 1/above/hotcheck Karen 1/4/hotcheck Karen .above/1/2/3/4/ 1 and 1/4. 1 and 1/2. 1 and 3/4. 2 -2 -3 -4 -5 -6 -8 -10 -12 -14 -16 -20 -24 -28 -32 20-30 30-40 40-65 60-85 75-125 150-250 200-350 300-500 500-600 500-700 600-900 600-900 850-1050 950-1150 90-100 135-150 180-200 270-300 450-500 650-700 900-1000 1000-1100 1200-1400 1200-1400 1500-1800 70 100 210 300 500 700 120 250 420 480 850 1150 .above/hotcheck Karen /hotcheck Karen 3/4 / hotcheck Karen 1 and 1/4 1 and 1/2 1 and 3/4 3 and 3/4 5 7 8 // 1 / 1 / hotcheck Karen 1 and 3/4 2 .above/hotcheck Karen 2 / 3 and 1/2 4 .above/ 5 and 1/4 6 / 7 Figure 9-20 Flared fitting data Figure 9-21 and flared left and MS Pluralist fitting right MS Pluralist fittings MS Pluralist fittings are designed primarily for high pressure 3000 psi hydraulic systems that may be subjected to severe vibration or fluctuating pressure. Figure 9-22 Using this type of fitting eliminates all tube flaring, yet provides a safe and strong, dependable tube connection. The fitting consists of 3 parts: a body, a sleeve, and a nut. Figure 9-23 The internal design of the body causes the sleeve to cut into the outside of the tube when the body and nut are joined. The counterbore shoulder within the body is designed with a reverse angle of 15 degrees for steel connectors and 45 degrees for aluminum fittings. This reverse angle prevents inward collapse of the tubing when tightened and provides a partial sealing force to be exerted against the periphery of the body counterbore. Swaged fittings. A popular repair system for connecting and repairing hydraulic lines on transport category aircraft is the use of swaged trademark fittings. Swaged fittings create a permanent connection that is virtually maintenance-free. Swaged fittings are used to join hydraulic lines in areas where routine disconnections are not required and are often used with titanium and corrosion-resistant steel tubing. The fittings are installed with portable hydraulically powered tooling, which is compact enough to be used in tight spaces. Figure 9-24. If the fittings need to be disconnected, cut the tubing with a tube cutter. Special installation tooling is available in portable kits. Always use the manufacturer's instructions to install. 9-12. Sleeve MS20819. Union MS21902. Elbow MS21904. Adapter MS21900. Adapter MS21901. Union MS21903. TMS21905. Cross MS21906. Elbow MS21907. Elbow TMS21909. TMS21910. TMS21911. MS21908. Sleeve MS21922. Nut MS21917. Bushing MS21915. Plug MS21913. Union MS21924. TMS21912. Cap MS21914. Reducer MS21916. Nut MS21921. Adapter MS21923. Elbow MS21925. Elbow MS21926. MS21900-4D. Material: aluminum alloy size so fitting in 16 THS inch, /inch design part number, adapter. Pluralist tube to flared tube prefix, military specification. Figure 9-22. Typical MS Pluralist tube fittings. 9-13. Body nut. Lower die/holder assembly. Sleeve. Figure 9-23. Pluralist fitting. Swaged fittings. Typical PermaSwag trademark fittings are shown in Figure 9-25. One of the latest developments is the Permalite trademark fitting. Permalite trademark is a tube fitting that is mechanically attached to the tube by axial swaging. Permalite trademark works by deforming the fitting into the tube being joined by moving a ring, a component of the Permalite trademark fitting, axially along the fitting length using a PermaSwag axial swage tool. Typical Permalite trademark fittings are shown in Figure 9-26. Offutt fittings. Many transport category aircraft use Offutt fittings to join hydraulic lines in areas where routine disconnections are not required. Offutt fittings are standard fittings with a cryogenic sleeve. The sleeve is made of a shaped memory alloy, Tinel trademark. The sleeve is manufactured 3% smaller, frozen in liquid nitrogen, and expanded to 5% larger than the line. During installation, the fitting is removed from the liquid nitrogen and inserted onto the tube. During a 10 to 15 second warming up period, the fitting contracts to its original size, 3% smaller, biting down on the tube, forming a permanent seal. Offutt fittings can only be removed by cutting the tube at the sleeve, though this leaves enough room to replace it with a swaged fitting without replacing the hydraulic line. It is frequently used with titanium tubing. The shaped memory technology is also used for end fittings, flared fittings, and Pluralist fittings. Figure 9-27. Radial tubing installation and inspection. Before installing a line assembly in an aircraft, inspect the line carefully. Remove dents and scratches, and be sure all nuts and sleeves are snugly mated and securely fitted by proper flaring of the tubing. The line assembly should be clean and free of all foreign matter. Head assembly. Power unit. Hydraulic tubing. Waged fitting. Disconnect. Figure 9-24. Swaged fitting tooling. 9-14. Figure 9-25. PermaSwag TM fitting. Figure 9-26. Permalite trademark fitting. Figure 9-27. Offutt fittings. Connection and torque. Never apply compound to the faces of the fitting or the flare, as it destroys the metal-to-metal contact between the fitting and flare, a contact which is necessary to produce the seal. Be sure that the line assembly is properly aligned before tightening the fittings. Do not pull the installation into place with torque on the nut. Correct and incorrect methods of installing flared tube assemblies are illustrated in Figure 9-28. Proper torque values are given in Figure 9-22. Remember that these torque values are for flared type fittings only. Always tighten fittings to the correct torque value when installing a tube assembly. Over-tightening a fitting may badly damage or completely cut off the tube flare, or it may ruin the sleeve or fitting nut. Failure to tighten sufficiently also may do not deflect into place. Replace tube assembly. Incorrect. Will damage flare or threads, or cause sleeve to crack under vibration if tightened. Incorrect. May pull off or distort flare if tightened. Correctly fitted and tightened. 0.025 clearance between flare and shoulder before tightening. Figure 9-28. Correct and incorrect methods of tightening flared fittings. 9-15. Be serious, as this condition may allow the line to blow out of the assembly or to leak under system pressure. The use of torque wrenches and the prescribed torque values prevents over-tightening or under-tightening. If a tube fitting assembly is tightened properly, it may be removed and retightened many times before reflaring is necessary. Pluralist tube installation. Tighten the nut by hand until an increase in resistance to turning is encountered. Should it be impossible to run the nut down with the fingers, use a wrench, but be alert for the first signs of bottoming. It is important that the final tightening commence at the point where the nut just begins to bottom. Use a wrench and turn the nut 1/6 turn, one flat on a hex nut. Use a wrench on the connector to prevent it from turning while tightening the nut. After the tube assembly is installed, the system should be pressure tested. It is permissible to tighten the nut an additional 1/6 turn, making a total of 1/3 turn, should a connection leak. If leakage still occurs after tightening the nut a total of 1/3 turn, remove the assembly and inspect the components for scores, cracks, presence of foreign material, or damage from over-tightening. Several aircraft manufacturers include torque values in their maintenance manuals to tighten the Pluralist fittings. The following notes, cautions, and faults apply to the installation of rigid tubing. Note: over-tightening a Pluralist tube nut drives the cutting edge of the sleeve deeply into the tube, causing the tube to be weakened to the point where normal in-flight vibration could cause the tube to shear. After inspection, if no discrepancies are found, reassemble the connections and repeat the pressure test procedures. Caution: never tighten the nut beyond 1/3 turn, 2 flats on the hex nut. This is the maximum the fitting may be tightened without a possibility of permanently damaging the sleeve and nut. Common faults: flare distorted into nut threads, sleeve cracked, flare cracked or split, flare out of round, inside of flare rough or scratched, and threads of nut or union dirty, damaged, or broken. Rigid tubing inspection and repair. Minor dents and scratches in tubing may be repaired. Scratches or nicks not deeper than 10% of the wall thickness in aluminum alloy tubing, which are not in the heel of a bend, may be repaired by burnishing with hand tools. The damage limits for hard, thin-walled corrosion-resistant steel and titanium tubing are considerably less than for aluminum tubing, and might depend on the aircraft manufacturer. Consult the aircraft maintenance manual for damage limits. Replace lines with severe die marks, seams, or splits in the tube. Any crack or deformity in a flare is unacceptable and is cause for rejection. A dent of less than 20% of the tube diameter is not objectionable, unless it is in the heel of a bend. To remove dents, draw a bullet of proper size through the tube by means of a length of cable, or push the bullet through a short straight tube by means of a dowel rod. In this case, a bullet is a ball bearing or slug normally made of steel, or some other hard metal. In the case of soft aluminum tubing, a hardwood slug or dowel may even be used as a bullet. Figure 9-29, a severely damaged line should be replaced. However, the line may be repaired by cutting out the damaged section and inserting a tube section of the same size and material. Flare both ends of the undamaged and replacement tube sections, and make the connection by using standard unions, sleeves, and tube nuts. Aluminum 6061-T6, corrosion-resistant steel 304-1/8H, and titanium 3AL-2.5V tubing can be repaired by swaged fittings. If the damaged portion is short enough, omit the insert tube and repair by using one repair union. Figure 9-30, when repairing a damaged line, be very careful to remove all chips and burrs. Any open line that is to be left unattended for some time should be sealed using metal, wood, rubber, or plastic plugs or caps. When repairing a low-pressure line using a flexible fluid connection assembly, position the hose clamps carefully to prevent overhang of the clamp bands, or chafing of the tightening screws on adjacent parts. If chafing can occur, the hose clamps should be repositioned on the hose. Figure 9-31 illustrates the design of a flexible fluid connection assembly and gives the maximum allowable angular and dimensional offset. When replacing rigid tubing, ensure that the layout of the new line is the same as that of the line being replaced. Remove the damaged or worn assembly, taking care not to further damage or distort it, and use it as a forming template for the new part. If the old length of tubing cannot be used as a pattern, make a wire template, bending the pattern by hand as required for the new assembly. Then bend the tubing to match the wire. Dent cable. Bullet. Figure 9-29. Dent removal using a bullet. 9-16. Type of failure repair method. 1. Pinhole leak or circumferential crack in tubing. 2. Longitudinal crack in tubing, crack length in excess of 0.30. New section. Original tubing. 3. Leaking T or elbow, permanent tube connection type. 4. Leaking flared, flirtless, or lip seal end fittings. not to exceed 0.30. Make 1 or 2 cuts, as necessary, to remove damaged section. If 2 cuts are required, the distance between them shall not exceed 0.30. If distance is more than 0.30, go to repair method 2. B. Swage 1 tube to tube union in tube section under repair. Make 2 cuts to enable removal of damaged section. B. Remove damaged section and duplicate. C. Swage replacement section into tubing under repair using 2 tube to tube unions. Cut out defective T or elbow. B. Duplicate tubing sections for each branch. C. Swage splice sections to T or elbow. D. Connect each splice section to tubing under repair using a tube to tube union. Cut tubing to remove defective fitting. B. Swage appropriate end fitting to tube end. C. Connect new end fitting to mating connection, torquing nut as required. Figure 9-30. From a swage trademark repair. Pattern. Never select a path that does not require bends in the tubing. A tube cannot be cut or flared accurately enough so that it can be installed without bending, and still be free from mechanical strain. Bends are also necessary to permit the tubing to expand or contract under temperature changes, and to absorb vibration. If the tube is small, under 1/4, and can be hand-formed, casual bends may be made to allow for this. If the tube must be machine-formed, definite bends must be made to avoid a straight assembly. Start all bends a reasonable distance from the fittings, because the sleeves and nuts must be slipped back during the fabrication of flares and during inspections. In all cases, the new tube assembly should be so formed prior to installation that it is not necessary to pull or deflect the assembly into alignment by means of the coupling nuts. Flexible hose fluid lines. Flexible hose is used in aircraft fluid systems to connect moving parts with stationary parts in locations subject to vibration, or where a great amount of flexibility is needed. It can also serve as a connector in metal tubing systems. Hose materials and construction. Pure rubber is never used in the construction of flexible fluid lines. To meet the requirements of strength, durability, and workability, among other factors, synthetics are used in place of pure rubber. Synthetic materials most commonly used in the manufacture of flexible hose are bunion, neoprene, butyl, ethylene propylene thin rubber, EPM, and Teflon trademark. While Teflon trademark is in a category of its own, the others are synthetic rubber. 9-17. Clamps. 1/4 minutes. G-ref. Fitting hose. Tubing. 3 degrees max. Angular deviation. Max. Offset. Minimum gap, G, shall be 1/2, or tubo D/4. Figure 9-31. Flexible fluid connection assembly. Bunion. Bunion is a synthetic rubber compound that has excellent resistance to petroleum products. Do not confuse with Bunias. Do not use for phosphate ester base hydraulic fluid. Skydrol trademark. Neoprene. Neoprene is a synthetic rubber compound that has an acetylene base. Its resistance to petroleum products is not as good as Bunion, but it has better abrasive resistance. Do not use for phosphate ester base hydraulic fluid. Skydrol trademark. Butyl. Butyl is a synthetic rubber compound made from petroleum raw materials. It is an excellent material to use with phosphate ester base hydraulic fluid. Skydrol trademark. Do not use with petroleum products. Flexible rubber hose consists of a seamless synthetic rubber inner tube covered with layers of cotton braid and wire braid, and an outer layer of rubber impregnated cotton braid. This type of hose is suitable for use in fuel, oil, coolant, and hydraulic systems. The types of hose are normally classified by the amount of pressure they are designed to withstand under normal operating conditions: low, medium, and high. Low pressure. Below 250 psi. Fabric braid reinforcement. Medium pressure. Up to 3000 psi. 1-wire braid reinforcement. Smaller sizes carry up to 3000 psi. Larger sizes carry pressure up to 1500 psi. High pressure. All sizes up to 3000 psi operating pressures. Flexible hoses used for brake systems have sometimes a stainless steel wire braid installed over the hose to protect the hose from damage. Figure 9-32. Hose identification. Lay lines and identification markings consisting of lines, letters, and numbers are printed on the hose. Figure 9-33. Most hydraulic hose is marked to identify its type, the quarter and year of manufacture, and a 5-digit code identifying the manufacturer. These markings are in contrasting colored letters and numerals that indicate the natural lay, no twist, of the hose and are repeated at intervals of not more than 9 inches along the length of the hose. Code markings assist in replacing a hose with one of the same specifications, or a recommended substitute. Hose suitable for use with phosphate ester base hydraulic fluid is marked Skydroll trademark use. In some instances, several types of hose may be suitable for the same use. Therefore, to make the correct hose selection, always refer to the applicable aircraft maintenance or parts manual. Teflon trademark is the DuPont trade name for tetrafluoroethylene resin. It has a broad operating temperature range, -65 degrees Fahrenheit to +450 degrees Fahrenheit. It is compatible with nearly every substance or agent used. It offers little resistance to flow. Sticky, viscous materials do not adhere to it. It has less volumetric expansion than rubber, and the shelf and service life is practically limitless. Teflon trademark hose is flexible and designed to meet the requirements of higher operating temperatures and pressures in present aircraft systems. Generally, it may be used in the same manner as rubber hose. Teflon trademark hose is processed and extruded into tube shape to a desired size. It is covered with stainless steel wire, which is braided over the tube for strength and protection. Teflon trademark hose is unaffected by any known fuel, petroleum, or synthetic base oils, alcohol, coolants, or solvents commonly used in aircraft. Teflon trademark hose has the distinct advantages of a practically unlimited storage time, greater operating temperature range, and broad usage. Figure 9-32. Flexible hose with stainless braid. 9-18. IMUL-H 8794 type hose. 2 cotton braids. Impregnated with synthetic compound. Hose number, hose size. MUL-H 8794. Size 6-290 SMFG symbol. Single wire braid, quarter and year of manufacturer, synthetic inner tube. B. MUL-H 6000 type hose. Views showing opposite side of hose. Hose size. Support wire. MUL-H 6000 size 3-490 SMFG symbol. Quarter and year of manufacturer. C. MUL-H 5593 type hose. Hose size, lay lines. MUL-H 5593-6-490 SMFG symbol. Quarter and year of manufacturer. D. MUL-H 27267 type hose. E. MUL-H 83797 type hose. Figure 9-33. Hose identification markings. Hydraulic, fuel, oil, coolant, water, alcohol, and pneumatic systems. Medium pressure Teflon trademark hose assemblies are sometimes performed to clear obstructions and to make connections using the shortest possible hose length. Since preforming permits tighter bends that eliminate the need for special elbows. Preformed hose assemblies save space and weight. Never straighten a preformed hose assembly. Use a support wire if the hose is to be removed for maintenance. Figure 9-34. Figure 9-34. Suggested handling of preformed hose. Flexible hose inspection. Check the hose and hose assemblies for deterioration at each inspection period. Leakage. Separation of the cover or braid from the inner tube. Cracks. Hardening. Lack of flexibility, or excessive cold flow are apparent signs of deterioration and reason for replacement. The term cold flow describes the deep, permanent impressions in the hose produced by the pressure of hose clamps or supports. When failure occurs in a flexible hose equipped with swaged end fittings, the entire assembly must be replaced. Obtain a new hose assembly of the correct size and length, complete with factory-installed end fittings. When failure occurs in hose equipped with reusable end fittings, a replacement line can be fabricated with the use of such tooling as may be necessary to comply with the assembly instructions of the manufacturer. Fabrication and replacement of flexible hose. To make a hose assembly, select the proper size hose and end fitting. Figure 9-35. MS-type end fittings for flexible hose are detachable and may be reused if determined to be serviceable. The inside diameter of the fitting is the same as the inside diameter of the hose to which it is attached. Figure 9-36. 9-19. 1. Place hose in vise and cut to desired length using fine-tooth hacksaw or cut-off wheel. 3. Place hose in vise and screw socket on hose counterclockwise. 5. Screw nipple into socket using wrench on hex of nipple. And leave .005 to .031 clearance between nipple hex and socket. 2. Locate length of hose to be cut off and slit cover with knife to wire braid. After slitting cover, twist off with pair of pliers. See note below. 4. Asterisk lubricant inside of hose and nipple threads liberally. Note. Hose assemblies fabricated per MUL-H 8790 must have the exposed wire braid coated with a special sealant. Note. Step 2 applies to hip pressure hose only. Asterisk caution. Do not use any petroleum product with hose designed for synthetic fluids, Skydroll trademark and or Hi-Jet product. For a lubricant during assembly, use a vegetable soap liquid. Disassemble in reverse order. Figure 9-35. Assembly of MS fitting to flexible hose. Flexible hose testing. All flexible hose must be proof tested after assembly and applying pressure to the inside of the hose assembly. The proof test medium may be a liquid or gas. For example, hydraulic, fuel, and oil lines are generally tested using hydraulic oil or water, whereas air or instrument lines are tested with dry, oil-free air or nitrogen. When testing with a liquid, all trapped air is bled from the assembly prior to tightening the cap or plug. Hose tests, using a gas, are conducted underwater. In all cases, follow the hose manufacturer's instructions for proof test pressure and fluid to be used when testing a specific hose assembly. Figure 9-37. When a flexible hose has been repaired or overhauled using existing hardware and new hose material, and before the hose is installed on the aircraft, it is recommended that the hose be tested to at least 1.5 system pressure. A hydraulic hose burst test stand is used for testing flexible hose. Figure 9-38. A new hose can be operationally checked after it is installed in the aircraft using system pressure. Size designations. Hose is also designated by a dash number according to its size. The dash number is stenciled on the side of the hose and indicates the size tubing with which the hose is compatible. It does not denote inside or outside diameter. When the dash number of the hose corresponds with the dash number of the tubing, the proper size hose is being used. Figure 9-33. Hose fittings. Flexible hose may be equipped with either swaged fittings or detachable fittings, or they may be used with beads and hose clamps. Hoses equipped with swaged fittings are ordered by correct length from the manufacturer and ordinarily cannot be assembled by the mechanic. They are swaged and tested at the factory, and are equipped with standard fittings. The detachable fittings used on flexible hoses may be detached and reused if they are not damaged. Otherwise, new fittings must be used. Figure 9-39. Installation of flexible hose assemblies. Slack. Hose assemblies must not be installed in a manner that causes a mechanical load on the hose. When installing flexible hose, provide slack or bend in the hose line from 5 to 8% of its total length to provide for changes in length that occurs when pressure is applied. Flexible hose contracts in length and expands in diameter when pressurized. Protect all flexible hoses from excessive temperatures, either by locating the lines so they are not affected or by installing shrouds around them. Figure 9-36. MS type end fitting. 9-20. Single wire braid fabric covered. Mil. Partno. Tube size OD, inches. Hose size ID, inches. Hose size OD, inches. Recom. Operating pressure. Psi. Units. Burst pressure. Psi. Max. Roof pressure. Psi. Units. Bend radius. Inches. ULH 8794-3L tilde/dot above/hotcheck.45, 3000, 12,000, 6,000, 3.00. ULH 8794-4L1/4 tilde/.52, 3000, 12,000, 6,000, 3.00. ULH 8794-5L Karen/1/4, 0.58, 3000, 10,000, 5,000, 3.38. ULH 8794-6L tilde/hotcheck Karen/.67, 2,000, 9,000, 4,500, 4.00. ULH 8794-8L1/2 dot above tilde/.77, 2,000, 8,000, 4,000, 4.63. ULH 8794-10L Karen/hotcheck 1/2, 0.92, 1,750, 7,000, 3,500, 5.50. ULH 8794-12L 3/4 Karen/hotcheck 1.08, 1,750, 6,000, 3,000, 6.50. ULH 8794-16L1/hotcheck 1.23, 800, 3,200, 1,600, 7.38. ULH 8794-20L1 and 1/4 1 dot above/hotcheck 1.50, 600, 2,500, 1,250, 9.00. ULH 8794-24L1 and 1/2 1 tilde/hotcheck 1.75, 500, 2,000, 1,000, 11.00. ULH 8794-32L2 1 dot above tilde/2.22, 350, 1,400, 713.25. ULH 8794-40L2 and 1/2 2 tilde/hotcheck 2.88, 200, 1,000, 300, 24.00. Mulage 8794-48L3, 3.56, 200, 800, 300, 33.00. Operating temperatures. Sizes 3 through 12. Minus 65 degrees Fahrenheit to plus 250 degrees Fahrenheit. Sizes 16 through 48. Minus 40 degrees Fahrenheit to plus 275 degrees Fahrenheit. Construction. Seamless synthetic rubber inner tube reinforced with one fiber braid. One braid of high tensile steel wire, and covered with an oil-resistant rubber impregnated fiber braid. Identification. Hose is identified by specification number, size number, quarter year and year. Hose manufacturer's identification. Uses. Hose is approved for use in aircraft hydraulic, pneumatic, coolant, fuel, and oil systems. Note: maximum temperatures and pressures should not be used simultaneously. Multiple wire braid rubber covered. Tube size, hose size recon. Minutes. Burst max. Proof minutes. Bend mill. Part no. ODI DOD operating pressure radius. Inches, pressure. Psi. Inches. Mulage 8788-4L 1/4/.63, 3016 8000 3.00. Mulage 8788-5L Karen/.70, 3014 7000 3.38. Mulage 8788-6L tilde/Hotcheck.above/.77, 3014 7000 5.00. Mulage 8788-8L 1/2/.86, 3014 7000 505.75. Mulage 8788-10L Karen/Hotcheck/1.03, 3012 6000 6.50. Mulage 8788-12L 3/4.above/1.22, 3012 6000 7.75. Mulage 8788-16L 1/Hotcheck 1.50, 3000, 10,000, 5,000, 9.63. Construction. Seamless synthetic rubber inner tube reinforced. Uses. High pressure hydraulic, pneumatic, coolant, fuel and oil. With one fiber braid. 2 or more steel wire braids. And operating temperatures. Minus 65 degrees Fahrenheit to plus 200 degrees Fahrenheit. Covered with synthetic rubber cover. For gas applications request perforated cover. Identification. Hose is identified by specification number, size number, quarter year and year. Hose manufacturer's identification. Figure 9-37. Aircraft hose specifications. 9-21. Figure 9-38. Hydraulic hose burst test stand. Spur. Socket. Nipple. Reinforcement sheath. Figure 9-39. Reusable fittings for medium pressure hose. Flex. When hose assemblies are subject to considerable vibration or flexing, sufficient slack must be left between rigid fittings. Install the hose so that flexor does not occur at the end fittings. The hose must remain straight for at least 2 hose diameters from the end fittings. Avoid clamp locations that restrict or prevent hose flexor. Twisting. Hoses must be installed without twisting to avoid possible rupture of the hose. For loosening of the attaching nuts. Use of swivel connections at one or both ends relieve twist stresses. Twisting of the hose can be determined from the identification stripe running along its length. This stripe should not spiral around the hose. Bending. To avoid sharp bends in the hose assembly, use elbow fittings, hose with elbow-type end fittings, or the appropriate bend roddy. Bends that are too sharp reduce the bursting pressure of flexible hose considerably below its rated value. Figure 9-40. Clearance. The hose assembly must clear all other lines, equipment, and adjacent structure under every operating condition. Flexible hose should be installed so that it is subject to a minimum of flexing during operation. Although hose must be supported at least every 24 inches, closer supports are desirable. Flexible hose must never be stretched tightly between 2 fittings. If clamps do not seal at specified tightening, examine hose connections, and replace parts as necessary. The above is for initial installation, and should not be used for loose clamps. For retightening loose hose clamping service, proceed as follows. Non-self-sealing hose. If the clamp screw cannot be tightened with the fingers, do not disturb unless leakage is evident. If leakage is present, tighten on a 4th turn. Self-sealing hose. If looser than finger tight, tighten to finger tight and add 1/4 turn. Figure 9-41. Hose clamps. To ensure proper sealing of hose connections, and to prevent breaking hose clamps or damaging the hose, follow the hose clamp tightening instructions carefully. When available, use the hose clamp torque limiting wrench. These wrenches are available in calibrations of 15 and 25 in pound limits. In the absence of torque limiting wrenches, follow the finger tight plus turns method. Because of the variations in hose clamp design and hose structure, the values given in figure 9-41 are approximate. Therefore, use good judgment when tightening hose clamps by this method. Since hose connections are subject to cold flow or a setting process, a follow-up tightening check should be made for several days after installation. Support clamps are used to secure the various lines to the airframe or power plant assemblies. Several types of support clamps are used for this purpose. The most commonly used clamps are the rubber cushioned and clay. The rubber cushioned clamp is used to secure lines subject to vibration. The cushioning prevents chafing of the tubing. Figure 9-42. The plain clamp is used to secure lines in areas not subject to vibration. 9-22. Planning hose line installations. Wrong. Wrong right. Right. 1. Provide slack or bend in the hose line to provide for changes. 2. Observe linear stripe. The hose must not be twisted. High in length that will occur when pressure is applied. Pressures applied to a twisted hose may cause failure or loosen the nut. Wrong right. Wrong. 3. Relieve sharp bends. Avoid strain or hose collapse. And make right cleaner installations by using Aero-Quip elbows or other adapter fittings. Provide as large a bend radius as possible. Never use less than the recommended minimum bend radius specified for the hose. 4. Provide additional bend radius when lines are subject to flexing, and remember that the metal end fittings are not flexible. Place line support clamps so as not to restrict hose flexing. Figure 9-40. Flexible hose installation. Initial installation only. Self-sealing hose approximately 15 in pounds. All other aircraft hose approximately 25 in pounds. Worm screw type clamp, 10 threads per inch, finger tight plus 2. Complete turns. Finger tight plus 1 1/4 complete turns. Clamps, radial and other type, 28 threads per inch, finger tight plus 2 1/2 complete turns. Finger tight plus 2. Complete turns. Support tube at least 1/4, from edge of hole. Grommet. Figure 9-41. Hose clamp tightening. A Teflon trademark cushioned clamp is used in areas where the deteriorating effect of Skydroll trademark hydraulic fluid or fuel is expected. However, because it is less resilient, it does not provide as good a vibration damping effect as other cushion materials. Figure 9-42. Rubber cushioned clamp. Use bonded clamps to secure metal hydraulic, fuel, or oil lines in place. Unbonded clamps should be used only for securing wiring. Remove any paint or anodizing from the portion of the 9-23 tube at the bonding clamp location. Make certain that clamps are of the correct size. Clamps or supporting clips smaller than the outside diameter of the hose may restrict the flow of fluid through the hose. All fluid lines must be secured at specified intervals. The maximum distance between supports for rigid tubing is shown in figure 9-43. Tube OD, in. Distance between supports, in. Aluminum alloy steel. /9 1/2 11 1/2 dot above hot check 12. 14. 1/4, 13 1/2. 16. Karen / dot above hot check 15, 18. / 16 1/2. 20. 1/2. 19. 23. Karen / 22, 25 1/2 3/4. 24. 27 1/2. 1. 26 1/2. 30. Figure 9-43. Maximum distance between supports for fluid tubing. 9-24. Chapter 10. Inspection Concepts and Techniques.